At this point, we've done most of the legwork to describe what we are about to implement in code. Now we just have to discuss a little more about what the code is going to look like, and then we can look at the actual code. So let's again recap all the usual steps in the context of our data and our new model. So step number 1 is to load in the data. For the coming example, we'll be looking at the classic MNIST dataset, which is a dataset containing handwritten digits. Our job is to accept as input an image of the digit and then classify what the digit is. Since there are 10 possible digits, 0 up to 9, this is a multi-class classification problem. Also note that even though these data are technically images, they don't come from actual image files like JPEGs or PNGs. Instead, the MNIST dataset is actually already included in the Torch Vision library, which makes things a little bit more convenient for us. Also, they are grayscale images, so we don't have to worry about color right now. Later in the course, we'll look at how to load in actual image files. Step number 2 is to build our model. As per this section of the course, the model is a feed-forward neural network. Basically, it's going to be multi-class logistic regression with a few more layers before it, all chained together sequentially. Step number 3 is to train the model. Now, this is the beauty of deep learning and deep learning frameworks. There is zero additional work to do here. All we have to do is pretty much the same training loop we have already seen, although there is one small modification we are going to make in order to improve the training process called batch gradient descent. We'll see what that is later on in this lecture. Step number 4 is to evaluate the model. Again, this is exactly the same. You could say that these steps are model agnostic. They don't care what the actual form of the model is. Step number 5 is to use the model to make predictions. We'll do something interesting in this section, which will be to look at which predictions the neural network is getting wrong. This might give us some insight on why the neural network is doing what it's doing. So let's start by breaking down step number 1. As mentioned, this data is going to come from the PyTorch library itself, which will keep things simple for us. Actually, to be more specific, it comes from a sister library called Torch Vision, which you normally have to install separately. But since everything is installed for you in Google Colab, we won't need to worry about that. Torch Vision specializes in providing functionality for, you guessed it, machine vision. This includes both helper functions and datasets, of which we'll see multiple in this course. Of course, one of these datasets is the famous MNIST dataset, which is a standard machine learning benchmark of handwritten digits. This is an image classification problem, so the data are images, and the targets are what the image is of. Each image is the same size, 28 by 28 pixels, which is equal to 784 pixels in total. The MNIST dataset contains only grayscale images, so the images are just of size 28 by 28 and not 28 by 28 by 3, which is what they would be if they had color. A grayscale image is pretty basic. Just imagine it like a matrix of numbers. The number in each element of the matrix tells us how dark or how light that pixel should be. So if you have a very small number, close to 0, you'll get a very dark color like black. If you have a very large number, close to 255, you'll get a very light color, close to white. When we call the function torchvision.datasets.mnist and pass in train equal to true, we get back a training dataset object, which is similar to what we saw in scikit-learn. Specifically, if we call the data attribute, we get the input data, which are the images. And if we call the targets attribute, we get the targets, which are the labels, telling us what digit the corresponding image is of. We can think of trainDataset.data as xtrain and trainDataset.targets as ytrain. So xtrain is of shape n by 28 by 28, whereas ytrain is a 1D vector of length n. In our case, n is equal to 60,000. Correspondingly, if we call the same function, torchvision.datasets.mnist, but we pass in a train equal to false, then we'll get back the test dataset. As before, we can call testDataset.data to get xtest, and we can call testDataset.targets to get ytest. X-test is of size n-test by 28 by 28, and Y-test is a 1D vector of length n-test. And in our case, n-test is 10,000. As a reminder, the image pixels are stored as integers from 0 to 255, so we'll have to scale them to go from 0 to 1. This is because we like the input data into a neural network to be in a small range, as you recall. In addition, the neural networks and other machine learning models that we have seen so far expect their inputs to be of shape n by d, which is a two-dimensional array. N is the number of samples, and d is the number of features. But as you just learned, our datasets come in the shape n by 28 by 28, which is a three-dimensional array. Therefore, we'll have to use the special view function in PyTorch to flatten the data into a two-dimensional array and treat each of the pixels as if they were an input feature. This is thanks to my rule, all data is the same. We don't care if this input represents a breast cancer feature vector or image pixels. Neural networks will work the same way regardless. Step number 2 is to instantiate the model. So first, let's start with the equation that represents how we get from the input to the output in our neural network. If we write it out all in one line, you can see that it follows the pattern inside to outside. That's just your basic order of operations for arithmetic. But we can split it up into intermediate variables so that we can see each step one at a time. So A1 is equal to W1 times X plus B1, Z1 is equal to sigma A1, A2 is equal to W2 times Z1 plus B2. And then technically Y is equal to softmax of A2, but remember that we omit this step in PyTorch because it's already included in the loss function. One important thing to note is that even when we use an activation function such as the rel-u, we often still write it as sigma when we write down the math. So that's just something to keep in mind for the future so you don't get confused when you see it. Basically, the important thing to remember is that each of these math equations is just an object in PyTorch. So we have nn.linear 784, 128, nn.rel-u, and a final nn.linear 12810. As mentioned previously, rel-u is a fine default choice. But you might be wondering, why did I choose the value 128? And of course, there is no special reason. This is just a matter of hyperparameter selection, for which you should use trial and error, as well as past experience to guide your decisions. You might also notice that, oddly, I had to specify the number 128 twice. This makes sense because if the output of the first layer is 128, and that's the input to the next layer, then the next layer must also have input size 128. But it also does not make sense in the sense that this is totally redundant. For example, in TensorFlow 2 or Keras, you only have to specify this number once. And it also leads to more opportunities for error. If you specify different numbers, your program simply won't run. You'll notice that the same theme will apply to later sections of the course as well, and this gets especially complicated for convolutional neural networks. Finally, there are 10 outputs because there are 10 classes, which correspond to the 10 digits 0 up to 9. Step number 3 is training the model. This will almost be the same loop as we had previously, but with one additional detail. Previously, on each epoch, we took the entire dataset, made a prediction on it, and then calculated the loss and did gradient descent. But ask yourself, what if your dataset is actually too large to fit into memory? Previously, we just had a few hundred samples. Now we have 60,000. Today's datasets, such as the famous ImageNet dataset, have millions of images. ImageNet is approximately 150 gigabytes, which can't even fit on some laptop drives, never mind fit into memory. So clearly we need a better solution. The solution is batch gradient descent, and the idea is this. Let's suppose we split our data up into batches. Then, instead of having just one loop over each of the epochs, we'll have a nested loop over each batch. Then we'll do all our usual steps on that small batch, rather than over the entire dataset. That includes zeroing the gradient, calculating the outputs for that batch, calculating the loss, and doing one step of gradient descent. In fact, batch gradient descent is such a fundamental part of deep learning that the PyTorch library comes with a data loader class, which comes with a batch size argument and acts as a generator over the dataset. So although in my in-depth courses I will teach you how to write a batch gradient descent loop by yourself, in PyTorch we can just loop over a data loader object and it automatically yields batches of inputs and targets. The next question to consider is, why does this work? Why is it okay to do gradient descent over batches instead of the entire dataset? Here's some intuition. Suppose we want to know the average height of all human beings on Earth. Think about why that would be an infeasible task, just like how storing all of ImageNet in memory is infeasible. Well, there are 7 billion people currently on Earth. You can't possibly ask them all how tall they are. Therefore, we have to do what all scientific experiments do: take a random sample from the population. This is what scientists do when they want to test drugs or when they want to do a psychology experiment. They can't possibly ask everyone in the world to participate in their experiment, so they have to choose just a small sample of people and generate statistics based on this sample only. At the same time, do we not expect that this sample represents the true population? The answer is usually yes. Do we expect that our measurements on the sample will be close to the measurements we could theoretically take on the entire population? The answer is yes. The same thing happens when we do batch gradient descent. Even though we are only looking at a small sample of the data at any given time, we do expect that the loss and its gradient will be representative of the entire dataset, which itself is what we expect to be representative of the true distribution of where the dataset comes from. Furthermore, on each epoch, we still see every data point, so we don't miss anything, unlike real-world population samples. Finally, step 4 and step 5 are to evaluate the model and make predictions using the model. As we just discussed, with large datasets, it may not be feasible to load in the entire dataset into memory. Therefore, we can't just do model of inputs and pass in the entire dataset all at once. And so this is yet another place where we have to make use of our data loader object. Due to the fact that our predictions come in batches, we won't just have a single array of predictions to compare to the targets like we did before. One way we can get around this is to just apply the definition of accuracy directly and calculate it ourselves. For each batch, we get the predictions and the targets. We don't want the accuracy on this batch only, but what we can do is count up the number of predictions we got correct. If we tally up how many we got correct and how many samples we saw in total, then we can just divide the number correct by the number total once the loop is over, and that's our accuracy. Another complication is how we actually make predictions in the first place. Recall that we are no longer doing binary classification, so it's not a matter of just checking whether the output is greater than 0 or less than 0. Instead, the output is of size k, where k is the number of classes. As you know, these k outputs will theoretically be passed through a softmax function to give us the probability that the input belongs to each of these k classes. But do we need these probabilities? Well, just like with binary classification, the answer is no. Why is the softmax function called softmax function in the first place? It's because it's kind of like the max function, except that instead of just telling us which element is the biggest, it just weights each of the elements relative to each other. In other words, a soft version of the max. In other words, the maximum value before we do the softmax will still be the maximum value after we do the softmax. It's just that the softmax happens to map those values to probabilities. Therefore, we just need to pick which of the k outputs has the maximum value and not worry about them being probabilities or not. In PyTorch, this is accomplished with torch.max, which returns both the maximum value and its index. And because we're doing classification, we're actually interested in the index and not the value itself.